Hey everyone and welcome. If you're revising for your GCSE Physics exam, you have come to the perfect place. We're about to get stuck into a really important higher tier topic, momentum. We're going to see how it explains everything from what happens in a car crash to why playgrounds are designed the way they are.
But before we dive into any equations or definitions, let's start with something you've probably felt yourself. You're in a car. The driver brakes suddenly, and you feel that seatbelt pull tight and lock you in place. Why does it do that? And how does that simple mechanism actually save your life? Well, the answer to both questions is all about the physics of momentum. So here's our game plan for this explainer. We're going to build this up step by step. First, we'll nail down what momentum actually is. Then, we'll look at the golden rule that governs it, the law of conservation. We'll see that law in action in collisions, link it all up to the idea of force, and then, finally, we'll have all the tools we need to answer that big question about how seatbelts and other safety features work. All right, let's jump right in. First things first, what exactly is momentum? Okay, the absolute first thing you need to get is that momentum is all about things that are moving. If an object is standing still, its momentum is zero. It's as simple as that. The way we calculate it is just by multiplying its mass by its velocity. And here is the equation you're going to be using all the time. P equals m times v. Now, P is what we use for momentum, and we measure that in kilogram meters per second. M is for mass, which has to be in kilograms, and V is for velocity in meters per second. And hey, quick exam tip for you. Just making sure your units are correct is such an easy way to pick up extra marks, so don't forget it. Right, and it's super important not to get momentum and mass mixed up. Mass is just the amount of stuff something's made of. You know, a parked bus has a huge amount of mass, but because it's not moving, it has absolutely no momentum. Momentum is what we call mass in motion. And because velocity has a direction, that means momentum does too. It's a vector quantity, and that little detail, well, it's actually a really big deal. Okay, let's move on to what is honestly the single most important rule for this entire topic. If you understand this, you can solve pretty much any problem they throw at you. It's the law of conservation of momentum. So the law says that in a closed system, and for your exam, that basically just means we're ignoring things like friction and air resistance, the total amount of momentum you start with before an event is exactly the same as the total amount you have after it. It doesn't matter if it's two things crashing into each other or something exploding outwards, momentum doesn't just disappear. It's just shared out differently between the objects. So, how do you actually use this in an exam question? Well, it's a pretty straightforward three-step process. Step 1, you calculate the total momentum of everything involved before the collision or explosion. Step 2, you just remember that that total number must be the same after the event. And step 3, you use that fact to solve for whatever piece of information is missing, which is usually the final velocity. Okay, theory's great, but let's actually put that three-step process to the test and see how it works in a classic exam scenario, a collision. So picture this. We've got a car, it has a mass of 1,000 kilograms, and it's moving along at 10 meters per second. It then crashes into an identical car, which is just sitting there, stationary. After the crash, the two cars get tangled up and move off together. We can use our law to figure out exactly how fast they're moving. All right, let's break this down. Before the collision, only the first car is moving. Its momentum is its mass, 1,000 kilos, times its velocity, 10 meters per second. So that's 10,000. The second car isn't moving, so its momentum is 0. That means our total momentum before the crash is 10,000 plus 0, which is just 10,000. Now, our law of conservation tells us the total momentum after the crash must also be 10,000. But now, the two cars are stuck together, so their combined mass is 2,000 kilograms. To find the new velocity, we just rearrange our equation. Velocity is momentum divided by mass. So we do 10,000 divided by 2,000. And that gives us a final velocity of 5 meters per second. See? It works. So we've seen that in a collision, momentum is conserved. But hang on, what actually causes an object's momentum to change in the first place? Well, this is where force enters the picture. To really understand how force and momentum are linked, we're actually going to start with an old friend, an equation you definitely already know, Newton's second law. Force equals mass times acceleration. And the second piece of our puzzle is the definition of acceleration itself. Remember, acceleration is just the change in velocity, that's what the little triangle delta means, divided by the change in time. All right, now for the really clever part. We can take that definition of acceleration, the A, and just substitute it straight into Newton's second law. And when we do that, we get this new equation. Force equals mass times the change in velocity, all divided by the time taken. And this is brilliant. Have a look at the top part of that fraction, m delta v. That's mass times a change in velocity, which is just another way of saying a change in momentum. So this equation is telling us that force is equal to the rate of change of momentum. Let that sink in for a second. The big idea to take away is this. If you want to change something's momentum really quickly, you need a huge force. But if you can take your time and change the momentum slowly, you only need a small one. And that amazing idea brings us full circle, right back to our original question about seatbelts and car safety. This is how we apply all that physics to actually save lives.
Your GCSE specification actually requires you to be able to explain how a few common safety features work. Things like airbags and seatbelts, obviously, but also things like crash mats in a gym, cycle helmets, and even those soft cushioned surfaces you find in playgrounds. And the amazing thing is, they all rely on the exact same bit of physics. So how do all of these different things manage to reduce the force of an impact and stop people from getting hurt? The answer is actually incredibly simple, but it is so important. Every single one of those safety features, from an airbag to a squishy playground floor, works by doing the exact same thing. They all increase the time it takes for your momentum to change. They stretch out the impact over a longer period. Just think about it for a second. In any given crash, your change in momentum is basically a fixed value, right? Your mass isn't going to change, and your velocity has to go from whatever speed you were doing all the way down to zero. So that total change in momentum, the m delta v, is set in stone. So let's look at our key equation one last time. We know the top part of that fraction, the change in momentum, is fixed. But if a seatbelt or an airbag makes the bottom part of the fraction, the time, much, much larger, what happens to the overall force? Well, it has to get smaller. A much smaller force acting on your body means a much, much lower chance of serious injury. And that right there is the simple physics that saves lives every single day. So I'll leave you with this final thought to take away for your revision. Now that you know the principle, what other safety features can you think of from your everyday life, maybe in sports or even in packaging for fragile items, that you can now explain using this exact same concept? If you can start spotting it in the world around you, you'll have locked in this knowledge for your exam.